In the last section, we talked about how to evaluate the derivative at a certain point. So I could go and calculate f prime of 3, let's say, but if I had changed my mind like I did in that last video, if I said, oh, you know what, maybe I want to go evaluate f prime of 2 instead, we'd have to go and redo the whole entire problem, which is really tedious and pretty long. So in this section, we're going to talk about how to get around that. And we're going to talk about the derivative as a function. So the derivative of f, so here we're going to talk about the actual derivative, is f prime of x equals the limit as h approaches 0. And notice this is actually the same formula we had before. We're just using x in place of a. So we have f of x plus h minus f of x divided by h. So here is the definition of a limit. This is sometimes called the limit definition of a derivative. If f prime of if f prime of x exists, we say that f is differentiable at x, and if f is differentiable at every point of an interval I, we say that f is differentiable on I. So again, just a little bit of terminology here. Whenever we say something or a function is differentiable, we're saying, hey, the derivative exists at that point or on that interval. And we have all sorts of ways to talk about the derivative. So we could use f prime of x like we did right here. We could also use y prime if we have, say, y equals f of x. This one's a little bit different here. When we talk about dy over dx, or sometimes I'll just say that as dy dx, this represents really the instantaneous rate of change of y over the change in x here. This is actually my preferred notation for the derivative. We may say df dx, so this is kind of similar. Again, we're just talking about the instantaneous rate of change of f with respect to time, or with respect to x. And then this guy right here is a little bit different. I want to talk about it. And this guy right here, this d over dx, this has a fancy name. It's called the derivative operator. Derivative operator. And it's really telling you to do something. This says take the derivative of this function. So when I see something that looks like this, if I see d over dx of f of x, this is a statement. This says, hey, take the derivative, derivative of this function, of f of x. So it's telling you, hey, take the derivative of these functions. Whereas the first four right here, when we say y prime or f prime of x or dy dx or df dx, these all just represent the derivative. So it's almost a statement that says, hey, the derivative is whatever that is equal to. But this is actually a statement. This says, hey, the derivative, or go take the derivative of f of x and you'll get whatever that's equal to. So just be aware that we'll be using this derivative operator from time to time, and that just means, again, take the derivative of that function. So I'm going to look at a couple of examples here of just finding derivatives using this limit definition. I want to find the derivative of the function g of x equals negative x squared plus 2x minus 4. So now I'm going to basically use the same process I did before. So remember that limit definition. We said limit as h approaches 0. We said f of x plus h minus f of x divided by h. This is really similar to the definition that we used in the last section for the derivative at a point. Again, the only major difference here is we're using x rather than a. So we can approach it and break it down into the same 4 steps that we have been doing if you like it that way. Or if you want to try and evaluate it all at once, by all means, you can do that as well too. So I like to break it down into smaller steps. So I'm going to start with g of x plus h. I'm just going to start by looking at what is this piece right here. So g of x plus h, I'm just going to take out everywhere I have an x. I'm replacing it with x plus h. So I have opposite of x plus h quantity squared plus 2 times x plus h minus 4. And I'm going to take this and simplify it as much as I possibly can. Be careful with this negative sign right here. We do actually need to square this first before we apply that negative sign. So this really says the opposite of x plus h times x plus h. Over here I can take this 2 and distribute that. So this is 2x plus 2h minus 4. So I'm going to say, let's FOIL this out first. We're going to multiply these two together first before we worry about this minus sign. So when I do that, I should have x squared plus 2xh plus h squared plus 2x plus 2h minus 4. And now I will go ahead, take this minus sign and distribute it to the 3 terms that are in the parentheses, those 3 terms I get when I FOIL this out. So I end up with negative x squared minus 2xh minus h squared plus 2x plus 2h minus 4. Whew. Okay. If your step 1 is long, usually that's going to be the longest step. If your step 1 is actually pretty short, then you might want to be a little bit worried, because that usually leads to a more difficult problem. But here we have this big long statement. There are no like terms. Notice I actually can't simplify this anymore. There's nothing more I can really do with this. So we're just going to move on to the next step. So the next step, we have this. Now I'm going to subtract my original function f of x, or in this case g of x. So I always like to write down what we're doing. I'm going to take g of x plus h, which is what I just found, and subtract g of x. So g of x plus h, that's this whole big long mess. So that's going to be negative x squared minus 2xh minus h squared plus 2x plus 2h minus 4. And what I recommend you do for these problems is you use parentheses around each of these. I think, for one, it makes it easier to see the substitution that you're actually making. And I'll talk about the second reason here in just a second. Minus g of x. Well, g of x is actually just our original function up here. That's negative x squared plus 2x minus 4. So minus negative x squared plus 2x minus 4. Now, if I don't put parentheses around this guy right here, I'm not going to know that, hey, I need to take this minus sign. I'm really subtracting each one of these 3 terms, and I won't know that I need to distribute that minus sign to each of those terms. I might just subtract that first term and then kind of mess up the other ones. So I need to make sure that this part right here is also in parentheses, so that I can say, hey, you know what, let's take this minus sign, let's distribute it through. I always change it to a plus and then change the signs on whatever follows the minus signs. And now we should have some terms that cancel out. So I see, hey, negative x squared plus positive x squared. Well, those two are going to cancel each other out. I see positive 2x plus negative 2x. Well, those two are going to cancel each other out. And I see negative 4 plus positive 4. Well, those two cancel each other out. All right, so let's see what we're left with. We've got a negative 2xh, we've got an h squared, and we've got a 2h. Once you get to this point, again, I can't simplify this really anymore. I say, all right, let's move on to the next step. So I now have my whole numerator. My next step is I need to divide by h. I need to add in this division by h. So I'm going to take what I found last time, which is g of x plus h minus g of x, take that whole thing and divide it by h. So I'm taking what I just found, negative 2xh plus h squared plus 2h divided by h. And here I want you to sort of be thinking about what the next step is going to look like. Remember, the next step is, hey, I want to take the limit as h approaches 0. If I try to take the limit as h approaches 0 of this statement, I'll tell you right now, you'll get 0 over 0. Remember, that's indeterminate form, and, well, we need to do more work. So my rule of thumb is, you know what? I'm going to try and get rid of this h in the denominator somehow, some way. 9 times out of 10, that's the end goal of these types of problems, is you need to get rid of that h in the denominator somehow. This one's not too bad though, because if I look at my numerator, hey, I've got a common factor of h. I can factor that out. So negative 2x plus h plus 2, all of this divided by h. And then look at that, h in the numerator, h in the denominator, those two cancel. So then step 4 says, all right, now let's take the limit as h approaches 0 of the whole thing, of g of x plus h minus g of x, all of this divided by h. So that I have negative 2x plus h plus 2 at the end of my last step. So I'm just plugging 0 in for h. So this says negative 2x plus 0 plus 2, or just negative 2x plus 2. At the end of this, once you work through all 4 of those steps, once you evaluate your limit, that's your derivative. So in this case, that is my g prime of x. So you might be thinking, well, gee, Mr. Huber, that's all well, and what makes this better than the last version that we just did? Why can't I just keep doing that same evaluating the derivative at a point? Well, what's really nice about this is, let's say I ask you to find g prime of 1. Well, that just means, hey, I'm going to take 1 and I'm going to plug it into my derivative function right here. So negative 2 times 1 plus 2, this is negative 2 plus 2 would give me 0. But remember at that last video there, I said if I change my x value, I'd have to redo the whole problem. That's not the case anymore. So if I change my mind and I said, you know what, I want to find g prime of negative 4, let's say, just to make a number up, well, I can just, again, plug that into this function here. So negative 2 times negative 4 plus 2 gives me 8 plus 2 would give me a positive 10 here. So this is really nice. I don't have to redo the whole problem. I just have to plug in a different x value to my derivative over here, which is really, really, really nice. It does make this process a whole lot easier and a whole lot smoother if we want to think about multiple x values here. One other thing that I'll mention, and notice that how this answer is different from the answers we came up with in the last section. This answer is actually a function, right? That's actually the name of this section. It says, hey, the derivative as a function, which means that at the end of the day, at the end of these problems, when you find your derivative, most of the time, not every time, but most of the time you end up with something in terms of x. You end up with something that depends on x. So when you find your derivative, you're not just going to say, oh, my derivative is 4 anymore. You're most likely going to end up with a function of x. So it could be 4x plus 2. It could be negative 8x squared plus 1. There's all sorts of different ways the derivative can look. So just be aware that our answers will look like functions of x rather than numerical values. But when you take a number and plug it into that derivative, that's when we end up with a numerical value. I want to look at one more here because finding the derivative is not always so straightforward. There are some examples that get a little bit tricky. So here I would like to look at h of x equals 2 square root of x plus 1. So if you need to off to the side, I might recommend actually just writing down that limit definition so that we can refer to it. So that limit as h approaches 0. And you know what? I'm already looking at this. I see h right here. I see h right here. I don't really want us to get confused by that. So let's just call this f of x instead. I just don't want to get confused. F of x, let's see, so this is f of x plus h minus f of x divided by h. So we have this, we can refer to it if we need to. You don't necessarily have to write it out though. So I'm going to look at f of x plus h. F of x plus h. So this is 2 square root of x plus h plus 1. Well, it's not like I can take this 2 and distribute it in there because those are under a radical. The 2 is not, so there's no like terms. I actually can't do anything, so cool. All right, I'm done with that. Move on to my next step then. My next step, well, I have this piece, I have f of x plus h. Now I'm going to subtract f of x. So, okay, let's subtract our original function. So f of x plus h minus f of x. I have 2 square root of x plus h plus 1 minus f of x, my original function, which is this guy up here, 2 square root of x plus 1. And again, I actually can't do anything with this, right? The radical that follows that first 2 is different than this radical right here, which means they're not like terms. I cannot combine these two things. There's nothing I can do here. So, okay, this seems fairly straightforward. Move on to step 3. Of course, when I say this seems fairly straightforward, you know, it's probably not going to be fairly straightforward coming up here. Next step, what do? I got to take what I just found and divide it by h. So, f of x plus h minus f of x, take that whole thing, divide it by h. So I'm going to take 2 square root of x plus h plus 1 minus 2 square root of x plus 1 divided by h. Remember last time I said your goal here most of the time is to get rid of this h, and that's still the case here. As it's written right now, it's not really a good way to do that. There's not much I can really do with this as it's currently written. So here's where we might need to start thinking outside of the box. The thing that I want to do in this problem is I'd really like to find a way to get rid of these radicals, because that's what's kind of causing a problem. That's what's keeping me from simplifying the numerator. I can't do anything with that. So some students will say, all right, well, if you just multiply it by 2 square root of x plus h plus 1 minus 2 square root of x plus 1, just do that to your numerator and your denominator, 2 square root of x plus h plus 1 minus 2 square root of x plus 1. That would get rid of the radical in the numerator. I'd say, well, it's a good try, but you're so close. You're so close, but no. I actually won't get rid of the radicals in my numerator. I'll still have a radical left over. If I want to get rid of radicals, I have two terms like this, I need to multiply by something called the, hopefully this sounds familiar, the conjugate. And the conjugate is very similar to this guy right here. The only thing I'm going to do is I'm going to take this minus sign, and I'm going to change it to a plus sign. So I have 2 square root of x plus h plus 1 plus 2 square root of x plus 1, and then same thing in the denominator because I want to keep this expression the same, so I need to multiply it by 1. Whatever I do to the numerator, I've got to do to the denominator as well. At this point, it's up to you how you want to approach it. I think there's a few different ways you could think about this. We could absolutely go and FOIL this out, and I think I probably will take that step here. You know what? Let's do that. I think I'm just going to FOIL out that numerator. It's going to be messy, but just try to follow along here. I'm going to try and go slow. I'm going to multiply, let's see, my first term. So 2 times 2, I've got 4. When I multiply square root of x plus h plus 1 times square root of x plus h plus 1, I should just lose the radical then. I'll just be left with x plus h plus 1. So, okay, there's my first term. My second term, 2 times 2, I have plus 4 again, times, let's see, square root, oops, let's get rid of that parentheses there. Square root of x plus h plus 1, and then times square root of x plus 1. It's not really a great way to simplify those two. You could FOIL that out if you want to, but I'm actually going to tell you right now it's more trouble than it's worth. Don't bother. You know what? I'm already worried about running out of space here, so let me clean this up a little bit. All right, so there's my first two terms. Let's see, next, negative 2 radical x plus 1 times 2 radical x plus h plus 1. I'll have minus 4 square root of x plus 1, square root of x plus h plus 1. Then here at the end here, negative 2 radical x plus 1 times positive 2 radical x plus 1. I've got minus 4 radical x plus 1 times radical x plus 1. Right, I'm multiplying these two terms together. Well, when I multiply those two out, it should just undo the radical. I'll be left with x plus 1. Denominator, I'm going to say, is actually a little bit easier. I'm going to tell you not to do anything to the denominator. So in my denominator, I still have h. So I've got h times, and I'm just going to leave this whole mess the same. I'm going to leave that as 2 square root x plus h plus 1 plus 2 square root x plus 1. So my numerator looks like a big old mess, and I need to think about how I can kind of fix this up. And actually, it looks really messy. It's going to simplify really, really nicely, because look at this. I've got 4 square root x plus h plus 1 times square root of x plus 1. Here I've got negative 4 square root x plus 1 times square root x plus h plus 1. I know I can multiply in any order that I like and end up with the same result. So this right here actually is the exact same expression as that term there. It's just I have one positive and one negative. Well, if that's the case, then those two terms should just cancel out. Okay, let's keep going with our numerator. 4, let's distribute that. I've got in my numerator 4x plus 4h plus 4 minus over here. Be careful with this negative sign right here. I'm really distributing a negative 4 over there, so minus 4x minus 4. Denominator, again, don't do anything with it. Just leave it as it is. It'll actually be harder at the end of the problem if you simplify it, so just leave it as it is for now. 2 radical x plus h plus 1 plus 2 radical x plus 1. Look at my numerator. What can I do here? Well, 4x minus 4x, those two cancel. 4 minus 4, those two cancel. What do I got? I'm left with 4h in my numerator divided by h times 2 radical x plus h plus 1 plus 2 radical x plus 1. And then hopefully we see this. Hey, look at that. I can cancel that h in my numerator and my denominator, which is exactly what I wanted to do. I'm left with 4 divided by 2 square root x plus h plus 1 plus 2 square root x plus 1. Holy moly, guys. I'm glad we're done with that problem. Oh wait, no, we're not done with that problem. That was just the end of step 3. Gotcha on that one. Step 4 then. Remember, what have we been doing this whole time? We have this. We just need to apply the limit statement now. So let's go and do that. Let's just apply the limit statement. This should go pretty quickly. Usually the last step is not going to give you a whole lot of problems if you've been simplifying along the way. So I want to look at the limit as h approaches 0. 4 over 2 square root x plus h plus 1 plus 2 radical x plus 1. And if you've been simplifying along the way, we should just be able to plug 0 in for h. So I have 4 over 2 square root x plus 0 plus 1 plus 2 square root x plus 1. Let's see, I've got 4 over 2 radical x plus 1 plus 2 radical x plus 1. So I've got 2 radical x plus 1 and another 2 radical x plus 1. Well, that's going to be 4 over 4 radical x plus 1. And if I can reduce that, that's 1 over square root of x plus 1. So that is my derivative. Holy moly. F prime of x is equal to 1 over radical x plus 1. There is my solution. Let me just double check. I didn't do anything silly. Nope, that is my answer. There we go. There's f prime of x. So some of these problems can get a little bit long. I will say this is kind of one of those tricks to have in your back pocket, this multiplying by the conjugate here. This is probably on the upper level of difficulty of problems that I would ask you to do using this limit definition of the derivative. This is probably like the hardest type of example that I would ask you to do. One other thing that I want to mention here is that when we FOILed out that numerator, another way you could have looked at it, so you could FOIL it out every single time, but I find that that process is kind of long and tedious, and to be frank, I'm kind of a lazy person. I look at this and I see, hey, 2 squared x plus h plus 1, 2 squared x plus h plus 1, this guy here and this guy, those are the same. How about I call that A and A. And 2 squared x plus 1, 2 squared x plus 1, well, those are the same. How about I call that B? I've got A minus B times A plus B. Well, I know that when I multiply A minus B times A plus B, that'll end up as a difference of 2 squares, A squared minus B squared. And that's exactly what I have right here. This is A squared. And this guy over here, that's B squared. So that is a shortcut you can take if you're multiplying by the conjugate. Otherwise, you can continue to FOIL those out if that's something that you feel more comfortable with. Again, I don't want you to feel too overwhelmed by this. This is a difficult problem. And I think that this is the hardest type of problem that I would ask you to do using this limit definition of the derivative. Square roots tend to be the most difficult. Polynomials, those are not going to give us too much trouble. Rationals, as we'll see an example of rational in the next video here. Those are kind of somewhere in between. But I would definitely take some time looking at limit definition of the derivative and applying that here, because I can promise that is something I'm going to ask about on that first exam.